Here we're going to be looking at some sample problems for tunneling phenomena, quantum tunneling. First, we're going to start with a rectangular potential. We're going to consider the deprotonation of an acid, basically thinking about that this proton has to overcome a certain barrier that keeps it attached to the rest of the molecule. Suppose that we can model that potential as being of a height of around 2 electron volts, and it extends over a certain length of 100 picometers. The question is, what will be the probability that this proton that has a certain amount of energy, close to that energy barrier, but not exactly the same as that, so still a smaller energy, what is the probability that this proton can actually be free and exist as a free proton in solution, for example? So obviously, this is a simplification of the model, but it's going to give us an idea of how tunneling is applied in this kind of proton transfer reactions. So the first thing that we have to think about is, okay, we're going to be using this rectangular potential barrier. We know what the formula for that transmission probability is. We have to go into a little bit of the details of the equations. For example, what is this kappa, what is this epsilon, what is this L, and so on. And that's what we have to discuss in this video. But before, in the previous video, I actually show you some of these plots of the transmission probability as a function of the incident energy, which is in this case the epsilon that I'm using in this formula. And this epsilon is nothing else other than the ratio between the energy of the particle with respect to the potential barrier energy. So the other parameters that we can see in this case is kappa. Kappa is going to be related to the mass of your particle and the potential difference between, or the energy difference between the potential barrier and the energy of your particle. And also you're going to include h bar in that parameter. Epsilon, as I mentioned before, is the ratio between the energy of your particle and the potential barrier. So now one thing that I'm going to suggest you specifically for whenever you want to plot these transmission probabilities is that instead of using this definition, you factor out the potential barrier. And when you factor that out, you end up with this expression, but this expression contains E over V, energy of your particle divided by the potential energy barrier, which is epsilon. Now, this one then will become 2mv, 1 minus epsilon, and then that's the one that you can actually use to then do these plots. So that little trick here is very important. Factor out v, 1 minus epsilon, so you can actually plot that easily whenever you have to do that with software. So it's something to have in mind. Now, how do we go about solving this problem? We already know what all of these parameters are, so we only have to do the proper substitutions. Now, remember that we have that value of kappa, we have the value of epsilon, we have everything that we need. We know that we are talking about a proton, so we can get the mass for that particle. We know what the potential barrier it is. In that case, we know what the energy of my proton is. It's given in the problem, so we can actually figure out all the different parameters that we need. So let's do some of the calculations with the proper substitutions. Since all the energies were given in electron volts, we can convert that energy difference into joules, which is not necessary, but depending on the type of problem that you have, you may need it in order to make the right dimension analysis. So we can calculate now kappa is 2 times the mass of the proton times the energy that we got from this energy difference between the potential and the kinetic energy and the energy of your particle divided by h bar. So you end up with this kappa that has units of inverse length that is in the order of 10 to the 10. So then we take kappa multiplied by the width of the potential barrier, and then we end up that this kappa times the length, which is this exponential, or this exponent in my exponential function, is going to be equal to 1.55. Now, 0.9975, that's going to be epsilon. This is basically telling you how close in energy is your particle with respect to the potential barrier. It's telling you this is roughly 99.8% of energy that the particle has with respect to the energy barrier. So under those conditions, we find that the transmission probability is roughly 0.2%. So most likely what we're looking at is in a plot that looks more like this than it looks like this, just because this transmission probability with the transmission probability is relatively small, even for whenever your particle has almost as much energy as the potential barrier. Okay, so this is one example using transmission probability in the square potential barrier. Please let me know if you have any questions, and I'll talk to you later.